Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start with the lecture 29 of our electrical machines subject. So today we will discuss about commutator and armature reaction. Before that, I gave you a question as homework and one question that we did which took a bit of long time. I want to discuss about that as well because I think few of you might get a different answer. So I want to put in front that answer as well, that solution as well, right? So before that, let's solve the homework question that I gave you. This was the question. So two DC machines A and B are made using same conductor material. So if they are made using same conductor material, that means the resistivity will be same. So resistivity of A will be equals to resistivity of B will be, let's say, resistivity, right? Their armature resistances are 0.4 ohm and 1.2 ohm. So their overall armature resistance, right, RA of the case A is 0.4 ohms for the machine A, and armature resistance of machine B is 1.2 ohms. Okay. Now what they're telling me, based on this information, which of the following is correct? Okay, machine A is larger than machine B for same current rating, same voltage rating, same current rating. Both machines are of same size. So many things are there, right? So how do I understand the size of a machine with all this? How do I understand that? So what you can do is you can understand how does my voltage and current rating depends on. What does my voltage and current rating depend? So current rating depends on area, right? So current rating, if the area of the cross section is larger, then it can support more current. That conductor can support more current. So current rating is proportional to area. What about voltage rating? Voltage rating, I know this very famous formula for voltage, right? Induced EMF of a DC generator, that is phi ZNP by 60A. So here, right, number of poles will always be fixed. If nothing is mentioned, assumption is number of poles is fixed. Let's say phi is also fixed, 60 and all these are same. So what are the mechanical parameters except the number of poles? That is Z and A, right? Parallel path, Z upon A, correct? Also, okay, sorry, it is proportional to area. Also, I can say current rating of machine is proportional to the number of parallel paths. More the number of parallel paths, more will be the current rating, right? If I have 6 parallel paths, if each coil can support 4 amperes, total will be 24 amperes of rating, right? If I have 12, then it will be higher. So this also is another proportionality, right? So I can say current rating is proportional to the number of parallel paths. Voltage rating is proportional to the number of conductors divided by the number of parallel paths. Okay, Z upon A. Okay, that is what my voltage rating and current rating is parallel to. Okay, so now what I can say, what can I say? Now what I can say is that uh, that I know they are made of same material and their resistance is different, right? What is resistance proportional to? Resistance, armature resistance is proportional to, if you remember, I derived the formula previously, it is Z by A square, right? And I know then it is equals to what? It is equals to Z by A into 1 by A, right? For one of the cases, if I assume for case, let's say B, option B, right? If I assume voltage rating to be same, if voltage rating is same, right, of both the machines, that means Z by A will be same for both the machines. So Z by A will be constant. That means if Z by A is constant, now I am doing for option B. For option B, Z by A will be same. That means I know this is given, right? The RA is this, RB is this, right? Armature resistance. So armature resistance of machine A is smaller than armature resistance of machine B. Okay, armature resistance of machine A is smaller than armature resistance of machine B. Okay, now I know Z by A is constant. So my, in this case, my armature resistance is proportional to 1 by A, right? So that means what? The number of parallel paths of path A will be this, right? And path B will be this. correct? So from here I can say that the number of parallel paths of path B will be less than number of parallel paths of path A. Okay, so number of parallel paths will be lower for same voltage rating. Number of parallel paths of machine B will be lower than machine A. Okay, so there are more number of parallel paths in machine A. If there are more number of parallel paths in machine A, then what does it mean? It basically means then the size will be higher, right? If I am accumulating more number of parallel paths, then size is higher, correct? So let me take few numbers, then also you will understand. So if I assume, let's say if I assume my Z to be, let's say 120, right? And if I assume my A to be Z by A to be, let me assume Z by A to be constant 10, right? So in this case, if Z by A is same for both of them, then okay, this A will be, if A is higher, B is also higher, will be higher. So if I assume the number of conductors in the machine, let's say A is 120, right? And Z by A is 10 assumed, right? I'm just assuming numbers here. So what will be the parallel paths of A? The number of parallel paths of A will be 12, right? What will be the number of parallel paths of B? So ZA is 120 and Z by A is this, right? So I have to assume a number for ZB as well. Okay, other than that I will not be able to do. But Z by A will be same. ZB also I should know. Else other than that I won't be able to figure it out. Okay, but number of parallel paths here will be something lower. So if I assume something like 10, right? If I assume this to be 10, so let me assume some number, right? If A is 12, so AB should be something lower, so it is 10. So what can be ZB? ZB ratio has to be mentioned, right? ZB will be 100. So we see only 100 conductors I have, and here I have 120 conductors, more number of conductors, right? More conductors I have. So in this case I have more number of conductors. So as I have more conductors, it will take up more space, correct? So more conductors for machine A. So more conductors machine A. Okay, hence bigger in size. Okay, now for, let's say, for the same current rating, because they are discussing about same current rating as well, so let us discuss the this was the case 1, same voltage rating. Okay, case 2, same current rating. Okay, case 2, same current rating. So if there are same current rating, what I told you, that current is proportional to the number of parallel paths, right? So I is constant, so A will be constant, right? A will be constant. Okay, so again, what information do I know? I know that my RA is less than RB, right? RA machine A is less than RA machine B, correct? Am I correct? Yes. So I know that this time A is constant. So if A is same, then what is my RA proportional to? RA is proportional to Z by A square, right? So I can directly write that as A is constant, I can say RA is proportional to Z only. Okay, simply, which has high number of conductors? So RB has high number of conductors. So machine B, so I can write from here that hence my ZB will be larger than ZA. Okay, hence machine B will be larger in size. Okay, so yeah, that was the solution for this particular question. So so if current ratings are same, machine B will be larger in size. So machine B will be larger. Machine B will be larger if same current rating. So option C is correct here. And if voltage rating is same, then machine A will be larger, I guess, right? Voltage rating is same. Machine A more conductor, so machine A will be larger for same voltage rating. So option B and C are the correct answer for this particular question. Okay, so now let's solve a question, similar question that we solved like previous lecture as well, where it took us a bit of time. So we will discuss that question as well. So we have a 4-pole DC generator, 1200 conductor, produces an open circuit voltage of 250. Okay, okay, open circuit voltage is 250. What are they asking? They are asking the calculate the average flux density produced. Okay, for pole arc to pitch ratio, this pole shoe diameter, this. Okay, pole shoe diameter they have given me, pole arc, pole pitch, all these things. Speed also they have given me. So how do I write no load open circuit voltage? It means basically whenever there is no load connected, what is the voltage generated by the your DC machine? It is 5 ZNP by 60. And what are they asking? They are asking the average magnetic flux density. So what is average magnetic flux density? Average magnetic flux density will be flux upon area. Total flux per pole upon area. Right? This will be the average magnetic flux density. So I know the open circuit voltage, right? I know the speed, I know the number of poles. Do I know whether it is lap or okay, DC generator, open circuit voltage, this. Okay, as they have not mentioned here that whether it is lap or like lap or wave winding, so I will assume it to be lap winding, because actually they should have mentioned here, right? Open circuit voltage is this, pole shoe diameter this. Yeah, no, it is mentioned, right? Sorry, it is mentioned, sorry, it is mentioned that it is lap connected, right? So yeah, it will be lap connected, so I don't even need to write. So P and A will be cancelled out. So Z also have they given me number, yeah, Z also they have given me. So that's why you should always write the data. So P is 4, Z is 1200, open circuit voltage EG is 250, your speed in RPM is 600 RPM. The pole shoe diameter, right? Pole shoe diameter is basically pole shoe diameter. They are telling us the pole shoe diameter. So I guess the pole shoe diameter they mean. What do they mean by pole shoe diameter? I guess this pole shoe diameter is meant by this, from the center of the armature. What is the diameter? That is what they mean. So this D is actually, this is not the pole shoe diameter. This should have been the armature diameter actually. Yeah, kind of wrong, because pole shoe diameter is, or is it correct? Yeah, this should have been the armature diameter. Yeah, here, right, this should have been the armature diameter. Just hold on. Armature diameter. Okay. Okay. So this D is 0.35, and the armature and the pole arc to pole pitch. What does pole arc to pole pitch means? It basically means pole arc means the angular distance covered by the poles, correct? And what does pole pole pitch basically means the absolute maximum that each pole can cover, right? Let's say I have total 6 poles. So what will be the pole pitch? So overall mechanically I have 360 degrees. So 360 divided by the number of poles will give me the pole pitch. This we have already learned, so I will not explain here, right? So in this case, the pole pitch, right? In this case, the pole pitch is 360 divided by 4, so it is 90 degrees. So I have 4 poles, right? So it will be 90 degrees. But they have given me the ratio of pole pitch to pole arc. Basically, this whole ratio divided by this whole ratio, that will actually provide me the total amount of area that this pole is coming under. Okay, so it is the ratio of pole arc to pole pitch. Okay, so pole arc to pole pitch is given as 0.7. Okay, armature length is 0.2 meters. Okay, this one was also was in meters only. Okay, this is in volts. Don't mess up the units, sir. Okay, okay, assuming they are lap connected, so that means basically my pole is equals to number of parallel paths. Calculate the average magnetic flux. So now I can finally proceed with the question. So I know all the values here, right? I know everything just except flux, because for finding B average I have to find out the flux per pole, right? So that is what I will proceed to. So 250 will be equals to phi, I don't know, number of conductors Z. Okay, number of conductors also they have provided, right? Sorry, it is 1200 conductors. Z is 1200. Speed is 600 rpm into P. Sixty into P, right? So basically your flux per pole will be equal to what? Your flux per pole, this will be 1025 divided by 1200, so 0.02 something like that. Okay, 0.02833. okay, this will be the flux per pole. Now B average will be the flux per pole divided by the area that it covers, right? So what is the area? So what is the area? Area under pole shoe cover, right? That is where the flux is getting distributed, correct? So that will be the flux density. So I know that if, let's say, I had this whole pole covered, right? This is the pole, correct? This is the pole shoe. So can anyone tell me how much area will this cover actually? Like how do I show it? So basically all the flux lines will come here, right? So how much area actually is it covering? How do I know how much area is it covering? So it is basically how do I say it? So this length is L, right? This length is L, okay, and this diameter is actually R. I mean radius is R, diameter will be D. That we know. How much length will it cover? So what will be this length? What will be this length? This length will be, this length is supposed to be 2 pi, not 2 pi r, sorry, r theta, right? R theta. So this, if I have a, what I am talking about, so let's say I have a circular section like this, right? So this is that circular section. This is that circular section, right? So if this is r and if this is theta, what will be this length? This length will be r into theta. Okay, r theta, correct? So, or small length is r d theta actually, but r theta we do multiply, basically multiply the angle, right? Now how much angle is this covering actually? That is what I have to find out. So I know the ratio of pole arc to pole pitch. I know pole pitch is how much? Pole pitch is supposed to be 90 degree, or in radians it is pi by 2. So my pole arc, because that is what I am interested in, because that is how much actual area my pole covers. So pole arc will be equals to 0.7 into pi by 2. Okay, so 0.7 into pi by 2, this will be pole arc. So my area under each pole shoe will be basically, this is the angle, right? This is the angle. It will be r into pole arc, correct, into length, because that was the this distance, and this distance is L only. So R will be what? D I have given, diameter they have given 0.35. So R will be 0.35 divided by 2 into pole arc. Pole arc is 0.7 into pi by 2 into length. Length is, I guess, 0.5, 0.2 meter. 0.2 meter. So what is the area? Everything is in meters here. So it is 0.35 divided by 2 into 0.7 into pi divided by 2 into 0.2, 0.0384. Okay, so 0.0385 meters square. Okay, just hold on. Yeah, sorry, just give me 1 second. I will just drink a bit of water. Yeah, so this will be 0.385. Now I can easily find the flux density. Flux density will be basically flux per pole divided by the area covered by that pole. So 0.02833, 0.0208833 okay, divided by the what do you call, the area, right? Area is 0.385. okay, so divide by 0.385, so this will be almost 0.01. okay, approximately 0.01 should be the answer. I'm just seeing whether I'm making any mistakes or not. 600, okay, 250 is there, and number of conductors is there, 4 will get cancelled, 60. Let me just check this. No, it is correct, only 0.0. This is correct, 0.0. Okay, anything, okay, maybe I have messed up here something, just hold on. 0.35 divided by 2 into 0.7 into pi divided by 2 into 0.2. yeah, sorry, I messed up a extra 0. There should have been an extra 0 over here. That is what I messed up. Okay, this should have been extra 0. This into 0.002833. yeah, 0.5413 Tesla. okay, so this will be the answer for this particular question. Now I will go back to that previous question, right? I will use the same method actually, because kind of same thing we are doing in that question, which we actually struggled for quite a while. So this was the question. So this was the question, right? If you remember, like all this information was given and I explained it quite a lot. So yes, there are, obviously you can solve it using a shortcut as well. So I will tell you the shortcut. I will say you the shortcut here. So they have directly given you the pole arc, right? Pole arc is directly given to you. Pole arc. So what you can do is, we have to find out the no load generated EMF. So I know the number of poles, I know the number of parallel paths, I know the total number of conductors, I know the speed of the armature, I know the length and this radius of the armature. Okay, I know the speed, I know everything. I just don't know the flux per pole, but I know the flux density. So I will go the other way around now. So what I will do is I will calculate flux now, flux per pole. Previously in this previous question that we just discussed, we calculated the flux density. Here I am calculating the flux per pole. So it is B average into area. Okay, B average into area. So this will be equals to 0.6 into, now this formula is something familiar to you, right? So armature is here, correct? And this is the pole basically. So this is basically the overall area or overall curve that a single pole is covering, right? Because let's say if I have 6 poles, then how much area, how much length in the radial direction a single pole will cover. Let's say I have 4 poles here, 4 pole here, 1 pole here, 1 pole here, 1 pole down, and 1 pole at here, right? So this will cover 1/4, this will cover 1/4, this will cover 1/4, this will cover 1/4. So overall circumference is 2 pi r. So this pole will cover 1/4 of the 2 pi r, this pole will cover 1/4 of the 2 pi r, this pole will cover 1/4, and so on, so right? That's why I am dividing here by 2 pi r, whole circumference divided by the number of poles. Okay. Now remember that my overall pole is totally not like, let's say if I have 4 pole, so each pole should cover mechanical 90 degrees, right? But here they have already told me that as it's a 6 pole machine, how much should each pole cover? 60 degrees. 360 divided by 6 is 60 degrees. But how much actually are they covering? 40 degrees. So they are covering something less, right? So the area covered also will be something lower, not exactly 60 degrees. That's why this ratio pole arc by pole pitch is there, to again further reduce this area, because this is the overall area that a single pole should cover, but actually a single pole does not have that much of pole arc, it is lower. So that's why it is pole arc by pole pitch. So this was the basically this curve length, right? This length r d theta basically, and this length is already L, right? This length is already L, that we already know. Okay, right? And this is this length that we are interested in. So if I replace plug-in values here, my flux per pole will come out to be 0.0418. In this question as well, if you would have calculated the flux per pole, it would have come out to be 0.01418. But then I am calculating the total number of conductors, that is 2 times the number of turns. So number of coils I had 240, and each coil had 2 turns. So overall my number of turns conductors will be 960. So if I plug in this formula, right, actually the value comes out to be 804.248, and this is actually, like, this is the book question. This is a question from a book, nothing to hide here. So this is the answer in the book, right? So they are just directly using the formula and that's it. But as I was trying to solve from the basics, right, I was not able to figure out where am I making a mistake. So if any of you guys know, comments below, you can tell me, like, I'm solving from basics, where am I making the mistakes? You guys can let me know. Somewhere I'm making the mistake, I don't know. Okay, so but this will be the answer actually, and this is how you can solve as well, right? Without knowing what is happening in the question, without knowing anything what is happening actually in the question, you can directly solve the question. Okay, so sometimes, yeah, formula approach will help in GATE examination. It might help, but understanding this also helps, right? If you don't understand this and directly skip on this, right, it will not always work for you. Someday you will be stuck. Okay, so just be careful while using this formulas directly. Okay, so now let's move on. So these 2 questions only took us 20 minutes. Okay, now let's actually move on to our actual topic, that is commutation, right? So we will discuss about commutation now. So what is commutation? Commutation, we have previously discussed that it refers to the reversal of current, right? So outside world sees this machine as DC, right? So it expects that current is unidirectional, but inside, I know that it is alternating. The voltage is alternating, so current also will be kind of alternating only, right? So in this cross section, the current is in this direction, and when the AB coil will reach here, current will be in the downward direction, correct? So current direction reverses, right? So that is what commutation do. Commutator helps us basically make it unidirectional. I have already explained the working, so I will just quickly go through it. I have already explained the working. So just before commutation, the current in the coil will be plus Ia by A, this coil, right? Just before commutation, and just after commutation, current will become minus Ia by A. How it works? this is a separate process, commutation. This we will discuss what are the disadvantages of commutation, what are the precautions that we have to take. We will discuss this in the next to next lecture, right? In not in today's lecture. Okay. So this we will learn. Don't worry. Okay. So commutation basically means that this, right? Here, where is the diagram? So here I have two brushes, right? And this coil is rotating. So it basically means that when this coil is in gap here, in the air gap, then again it reaches to this connection. So in that gap, right, there is huge current change, right? Because this was the direction, and as soon as it moved, the direction suddenly changed to this, right? Correct. This was the direction suddenly changed to this. So that change, that process of change is known as commutation. And what does it? Commutator does it. Okay. Commutator helps in the process of commutation. So commutator is this particular thing. These are brushes through which the current goes away, and commutator is the part, that is physical part, that is responsible for commutation. Okay. So slowly we'll see. So here, right, let's say at t equal initial position, if at initial position, when my, okay, I forgot to change the conductor here. No, yes I did, but I forgot to change the names here. Okay, this name should be here, right? So basically, when my conductor is in the north, facing the north pole, right? Conductor is facing the north pole, then I assume the EMF to be induced in the positive direction. Now, as soon as I move to the south pole, the current and the induced EMF is in the negative direction. Correct. Here also, like here, what is the direction of the induced EMF in the conductor? The direction of the induced EMF of the conductor will be this. Okay. And here, what will be the direction of the induced EMF of the conductor? It will be this. But what is the direction of the current? Direction of the current is in top. Right. This is the current direction. This is the induced EMF direction. Here, what is the direction of the current? Again, in the bottom. So the conductor is delivering power. That is fine. But the induced EMF in the single coil, right, changes. So this will be again. This will be A. This will be D, right? Okay. AD. Okay, I hope you have understood this very basic point. So what happens, what is happening, if you see here, the current direction was top, here the current direction bottom, here the induced EMF was in the top, here the induced EMF is in the bottom. So that is what is graphically shown here, right? So what happens if it's a perfect commutation? So the change in current, right, will be slow, and there would not be a sudden change in current from plus IA by A to minus IA by A, where IA by A is the current per parallel path or current per coil. Correct. But if it's a bad commutation, right, bad commutator, then current change will be drastic and there can be reactance voltage developed. But one thing you notice, it does not matter whether I am in first position or whether I am in the second position. What is the direction of the current here? If you see, the direction of the current here is always like this. What is helping? Which one is helping? This brushes, right? These brushes are helping me. If these brushes are not there, then the direction of the current also would have changed. But as brushes are there, as the commutator is there, what is happening? Here the current is unidirectional. Okay, here the current direction is unidirectional. So I hope you have understood this very basic point. So these are few theoretical points. A commutator is a cylindrical structure composed of multiple copper segments. We will discuss when we will discuss about commutation. Don't worry, physically also we will discuss. Each insulated from other mica sheets. So here each commutator will be insulated with mica sheets because there has to be a gap. Because this coil at case 1 will be connected to brush B1, at case 2 it will be connected to brush B2. That's how commutation works, because the current direction is unidirectional outside the brushes. To do that, I have to change the connection of the brushes. That is only possible if there is breakage in between, right? So basically what is happening is that, how can I show it? So these are my fingers, right? And this is the basically the commutator. So let's say one end of the commutator is here and the other end will be in the other end. So if let's say my this finger, right, this finger, okay, I will show in the camera this finger. So this finger and this finger both are rotating. This finger is both are rotating. Let's assume that the air is one of the ends of the commutator and my hand is one of the ends of the commutator, right? So if this finger rotates, what happens? The once my middle finger touches the air and again my middle finger touches the this hand, right? So what is happening? So once it is touching the brush B1 and the air is the brush B2, so that is how it is rotating, right? So once it will touch the brush B1, then it will touch the brush B2. So that is how it will rotate basically. So that is how the current direction is unidirectional, right? Because here the current direction changes in the conductor, but the brush connection also changes, like you can see, right? I hope you can see. So once I am touching this commutator one segment and then again I am rotating, so it is touching the air, so other segment. So that's how the current is unidirectional in the outside. So I have shown you practically as well how the current is unidirectional. So what is the function of commutator? So in generator converts internally AC generated voltage to DC. In motor converts the supplied DC to alternating current inside the armature. Because the DC machine actually, DC motor will not work if it does not have alternating induced voltage. That is the beauty, right? It is a DC machine, but it will not work. It will not work as a motor unless and until alternating voltage is induced in the coils, right? Because there will be no flux change, right? So if to generate the alternating coils, commutator do it. So if I keep on rotating the machine, what happens? Commutator also rotates and it generates a alternating voltage across it, plus EB and minus EB. That's it. Okay. So yeah, that's basically what commutation does. I hope you can understand. Right? Inside the coil, this is the coil voltage, and this is the output voltage. Output voltage is like this. So although the output voltage is not pure DC, it is pulsating DC. But we assume we just take the average value, right? So it is pulsating DC. This I have discussed in the first lecture as well. Pulsating DC. Okay. So same thing in DC generator, as armature rotates, the direction of the induced EMF in the armature conductors naturally reverses every half rotation due to Faraday's law, right? The commutator mechanically reverses the connection so that the output remains unidirectional. Okay, this entire process is called commutation. It's the same thing, nothing different here. So in DC motor as well, the same thing, you can go through and read over it. Okay, now one more important portion is where should I place the brushes, right? Because if you see, the commutator is here. What is a very good placement for carbon brushes? Why can I place the brushes, right? So that I can so that the machine can work in best efficiency, right? So carbon brushes are placed to maintain the sliding contact, right? So this commutator also rotates. So actually with the coils, right? Basically they are used to maintain this sliding contact. So what happens? Commutator is here, right? Commutator is here. So the commutator is actually also connected with this two rings, right? And ultimately brush is here. So there is friction between the brush and the commutator. That's why the name brush, because it is brushing the commutator, right? So it brushes the commutator. That's why the name is there as brush, as it brushes the commutator, right? So basically the brushes need to be very good and they need to be placed along the quadrature axis of the, okay, just hold on, what is happening here? It is actually wrong. It should be quadrature axis. That is what I'm trying to, yeah. Along the quadrature axis of the field poles. Why along the quadrature axis of the field poles? So ideally when I am doing the commutation, right? So let's say I am changing from brush B1 to B2, right? I'm changing the brushes. Ideally there should not be any induced voltage across the coils. If there is some induced voltage across the coils, what will happen? A short circuit current can flow through the path. Okay, a short circuit current can flow through the path, right? uh, what do I mean by it? So and also one more problem is there will be reactance voltage. So ideally, right, ideally when current should, ideally actually what they mean, ideally basically when this B1 and B2 should be swapped, basically when this air gap should come, right, this air gap or this, when this change of the current direction should come, it should come where the change in current is u. What do I mean by it? So if you see, the induced EMF is like this, and if I have a coil resistance of RC, right, RC is the coil resistance, what will the current? Current will be E upon RC, correct? Current on the coil will be E upon RC, correct? Now, if I change at this point or at this point, right, if I change at this point, so here there is some current, and this is a coil, this is a inductor, right, and this inductor, let's say, has some current I, and let's say when I'm changing from brush B1 to B2, there is a air gap, so suddenly the I changes to 0. So there is some delta I in very small amount of time, delta t, it is tending to 0, right? So that means a voltage will be induced. If you have studied inductor, that it is a coil, right? So there will be a reactance voltage, V will be equals to L dIL by dt. L dIL by dt. So V is equals to L dIL by dt. So that means it is basically equals to so L I don't know, but there is finite change of current in very small amount of time. So there will be reactance voltage will be developed, very high reactance voltage will be developed that can damage the coils. Okay, that's why we don't want this. That's why we place it in q axis, because if you remember, this is my north pole, right, and in the middle of the north pole where the magnetic flux is highest, it is the d axis, correct, and q axis is the place where the magnetic field is 0, that means the induced EMF is 0, right? That's why the brushes are placed in the q axis. Okay, carbon brushes are placed in the q axis, that is the reason. Okay, I hope you have understood this basic point. Yeah, same thing we will discuss, I guess. Yeah, electrically the brushes are considered to be in the interpolar region. What is interpolar axis? That also we'll understand when we will study just armature reaction. Just in the next few next few slides we will learn about armature reaction. Okay, interpoles, don't worry, you can ignore this, we will learn what are interpoles. Okay, so this is the summary table about commutator, and only this much theory is important for uh, commutation. Okay, so few more things are left for in case of the construction part. After that we will start our armature reaction. So this is the next portion. So just summarizing whatever we know, that a DC generator is a electromechanical device that converts mechanical energy into electrical energy through the principle of electromagnetic induction, right? Okay, when conductor moves in a magnetic field, the amount of magnetic flux linked with it varies with time because it is moving, so flux is changing, that links, flux that links the conductor is changing, hence the according to Faraday's law of electromagnetic induction, the changing of flux linkage induces an EMF. So the direction of the induced current will be given like this according to the Fleming's right hand rule, and for a motor it will be given according to the Fleming's left hand rule. Okay, this was the summary part about the motor and the generator, very basic thing. Just one more thing, few important equations for motor and generator. So for generator, the most important equation is the generated EMF, that is Eg equals to phi Znp by 60A, and for motor it is the torque equation, how much output am I getting, right? So for motor the equation will be somewhat like this. Here as well, one more thing to remember is what is the terminal voltage, right? Induced voltage and terminal voltage, right? So one more thing is that this is known as the, yeah, this is known as the terminal voltage, this is known as the generated voltage, right? These are the important things that you should keep in mind for a motor and a generator. Okay, now here for a motor, sorry, for a generator, for a motor mainly you have to discuss about the torque. Okay, so what is the torque developed? So torque developed we already know, power output will be given to you, power output will be Eb into Ia. So torque will be equals to omega m, mechanical into torque will be equals to the power output of the motor. Also we know that our torque is proportional to the armature current and the flux per pole. This is what my torque is proportional to. Okay, this is what my torque is proportional to. So these are the key points about motor and generator. Now back EMF, what is back EMF? Back EMF is just the opposing force that is there due to the torque, I mean due to the voltage that I apply, right? So otherwise how it will oppose? So as motor starts rotating due to electromagnetic torque, in EMF will be induced because a conductor, the flux linkage is changing inside the field. Of course EMF will be induced, right, as it cuts the magnetic field lines. So it will oppose its initial cause. What was happening? Initially it was rotating, so it will try to rotate it lower. Okay, so in starting, at the instant of starting, the torque will be very high, so it will try to rotate at very high speed. Okay, try to go to very high speed, but as back EMF will increase, so slowly the torque will reduce as current is reducing, hence the speed will be reaching steady state. So basically at starting, what is happening? Initially the machine is in off state. So if the machine is in off state, so my n will be 0. Okay, so if my n is 0, that means my induced EMF, back EMF will be 0. That means IA will be very high, right? Because what is IA? So I am providing, this is my motor, right, EB. Just I am drawing the motor and the supply part V. So IA will be V minus EB by R. Okay, V minus EB by R. So this is my IA basically. So as my EB increases, so my IA will reduce basically, correct, because everything else is constant. So here IA will increase, IA will be very high initially. If IA is very high, what is happening? The torque is very high, correct, torque is very high. If torque increases, the speed also tries to increase, right? Speed will try to increase. If speed increases, what? The back EMF will increase. If back EMF increases, then the current will reduce, and this is a feedback loop. At certain stage, it will reach steady state where my load torque will be equals to the developed torque. Then what will happen? The speed will be constant. At this point of time, the speed will be constant. So this is how a motor works. Generator working you already know. Just wanted to give you a brief about working of a motor. Okay. So yeah, I hope you have understood this basic point. Same thing is written over here. Same thing, whatever we have discussed is written over here. Now one more thing is there about brush drop. So if you see, right, my conductors are rotating and they are brushing the brush, right? So there is friction here. So due to that friction, there can be few losses. So all those losses are just assumed to be a drop across the brush. So it is known as the brush drop. Generally it is 1 to 2 volts. Okay. So voltage drop is called the brush drop and must be accounted for voltage equation. So overall, what will be the armature voltage equation? So in case of generator, in case of shunt generator, right, I will only derive for shunt generator. Overall voltage equation, EG has to provide the terminal voltage, of course, plus the drop across the armature, plus the drop across the brush. So all these drops the EG has to provide. For a shunt motor, my motor voltage or back EMF voltage will be what? The supply minus the drop across the armature minus the brush drop. Okay, so the voltage equation gets just a bit modified, that's it. Okay, that is what you have to keep in mind. Okay, so these are few materials which brushes are used for small machines, carbon copper compound brushes. For large machines, graphite, electrophite. So they support more current This will support lower amount of current because these are less costly. Why do we use carbon graphite brushes? Okay, because carbon is a self lubricating material, so even though there is wear and tear, it can lubricate itself. It has low friction, good conductivity, it has negative temperature coefficient, good thermal stability. So these are the material properties of carbon brushes, and these are the reasons why we use the carbon brushes as brush. Okay, so just summary, whatever we have been discussed till now, all those things are written over here, so you can just go through whatever we have discussed. The summary is written over here. Okay, now let's solve few basic questions, and after that we will start with our next topic, that is armature reaction. Okay, so the brushes used in DC machines are typically made of carbon, soft copper, hard copper. They are made of carbon, right? I just discussed that why we use carbon. Okay, rapid brush wear in DC machines can occur due to dust abrasion, extensive spring control, roughness of commutator segments. So actually it can, like if there is dust, right, there will be more friction. If you see that in your table, if there is more dust, you will see, if I just like what do you call, if I just place my mobile phone or just rotate or my move my mobile phone in the table, you will hear more sound. That sound is what, like sound energy lost due to friction, right? So if there is dust, there will be more friction, there will be more rapid wear. If there is excessive spring tension in the brushes, like excessive tension, then that can also damage. And roughness of the commutator segments, more roughness, thus friction increases. That is what we have learned in class 11, right? So of course all of the above will be the correct answer in this case. The number of brushes used in a commutator is determined by the number of brushes used in a commutator. How many number of brushes depend by the type of the armature winding used, whether it is lap connected or, sorry, not type of the armature winding, amount to be collected, right? Because if you remember, I will need more brushes, right? Number of brushes will be the equals to what, number of parallel paths. It does not depend on armature winding, how many parallel paths I have, right? Sorry, so how many parallel paths I have. Okay, so this will be equals to what, number of parallel paths is equals to what, is equals to the current rating, right? IE rating. So basically it depends on how much current I want to collect. So magnitude of the current to be collected. So option D will be the correct for this question. Now few theoretical questions. Why is it important to keep air gap in magnetic circuit of a DC machine? What does an increased air gap have on machine's operation? Because you might say, sir, there is air gap, so the magnetic flux will receive more reluctance, so the overall flux density reduces, hence the induced EMF also will reduce. You are correct, but still we have to provide air gap for safety concerns. So keeping minimum air gap in a DC machine's magnetic circuit is important because air offers higher reluctance compared to iron. A larger air gap increases the overall reluctance, demanding higher magnetizing current to maintain the same magnetic flux. This results in reduced efficiency and like bad effects, right? It may lead to lower torque output because the induced EMF will be lower, right? But why is it important? It is important because you have to provide that air gap, because for mechanical reasons we have to provide air gap. Okay, why? Because if I don't provide air gap, if they are very close to each other, one day if something messes up, right, if this armature moves just a bit, 1 to mm topwards, what will happen? It will just damage the like poles, right? Something will get damaged, either the armature will get damaged or the poles will get damaged. So of course I don't want this, right? So that's why we have to maintain proper air gap for physical mechanical reasons, for safety concerns, right? Safety of the machine, not yourself, of course for yourself and for the machine as well. Now why is it important to maintain proper alignment and firmly mount armature in a DC machine? What issue can arise due to misalignment? Okay, due to misalignment, right, what can happen is the air gap is not uniform anymore. The air gap is not uniform. If the air gap is not uniform, reluctance changes. If the reluctance changes, the flux density will not be uniform across different position of the armature. What can problem? If flux density is not uniform, it is not pure AC. If the waveform is not pure AC, so I mean there will be problem, right? Same thing is written over here. Waveform is not pure AC. If it is not pure AC, commutation also will not work properly. Many things will not work properly. So this uniformity helps preserve the consistent magnetic flux and reduces the energy losses. If armature is misaligned, it can cause uneven air gap leading to magnetic imbalance, higher losses, excessive vibrations. Because the AC component will, like harmonics are there, more AC components. So what will happen? It will vibrate more due to AC components. So yeah, these are the main thing. So that's why we don't want armature misalignment. Why is choosing right brush material important in a DC machine? What could happen if an unsuitable material is used? So if I don't choose a suitable material, the commutation will not work properly and the contact also is not proper. Then there will be many damages in the brushes, and if the brushes are damaged, that is the point from where I take the current as the output, right? So that also is not proper. Okay, so these are the problems basically. So selecting the proper brush materials is essential because it directly impacts commutation performance, contact efficiency, wear and tear, right? Of course it will lower the efficiency of the machine, it will lower the age of the machine, all those things will happen. So that's why maintaining proper efficiency is important. All these are interview questions. Okay, whatever we have discussed, these are for interview, right? Because this will not be asking gate obviously, but nowadays also they are asking MSQ, theoretical MSQ. So this can come, but mostly these are all interview questions. Okay, so now let's discuss about armature reaction. So what is armature reaction? To understand armature reaction, as the name suggests, it is the reaction by the armature. Reaction of what? Armature reaction is the reaction of the armature due to the main field flux. So if I copy this, right? If I copy this, and I know that this is not totally copied, sorry. I know that if I have a field, right? Magnetic field. If I have a magnetic field and if I have current carrying wires here, and if I'm rotating that prime mover, sorry, I phrased it wrong. If I have a magnetic field and I'm rotating the prime mover, then the flux, there is a flux cut, there will be induced EMF in the conductors. Due to that induced EMF, there will be currents in the conductors, right? So whatever the value of currents, I don't care, there will be currents. And due to the interaction of the current and the, due to that flux cut, current will be produced, EMF will be generated, and I will get the output voltage, right? So that's how electrical energy is generated, correct? Now there is a problem. If there is current flowing through the coils, what do you know? If I have a current carrying conductor, I know that current carrying conductor will have a magnetic field. That current carrying conductor will have a magnetic field around it. So if I have a current carrying conductor here, it will have its own magnetic field. That current carrying conductor will have its own magnetic field. If I can choose a color. So yeah, it will have either in the clockwise direction or in the anti-clockwise direction, depending whether it is inwards or outwards, right? So if I assume it to be in the clockwise direction, so what will happen? This is the magnetic flux periphery of this conductor, right? And already I have a magnetic flux. So the resultant magnetic flux direction will change. Resultant, due to this and this magnetic flux, the resultant magnetic flux direction will change. Okay, and that can have bad effects on the performance of the DC machine. So armature reaction is the effect of armature's magnetic field on the main field flux distribution. So there will be some main field flux due to which an armature EMF will be induced, and due to that armature will carry current. Okay, armature carries current which produces armature flux. Okay, armature flux it produces as it is current carrying wire, which then alters the main field flux, right? Which weakens, it can weaken or strengthen the main field flux. the main field flux. Okay, any one of them. So yeah, that is what we want to know, we want to understand. So for DC, like for DC generators, first of all we will decide how do I determine the current direction. For DC generator we use Fleming's right hand rule, for motors we use Fleming's left hand rule. In this lecture only we have discussed about that. So first of all let me decide the current direction, then I will decide the overall resultant flux direction. What will be the overall resultant flux direction? So what is the direction of the field, main field? Direction of the main field will be in this direction, right? Okay, so main field direction is in this right hand side direction from left to right. So that is my forefinger. So forefinger is the direction of the field, thumb is the direction of the torque. So in case of DC generator I am moving my moving this rotor in the clockwise direction. So for this conductor it is going upwards, right? So direction of the magnetic field, thumb, and the direction of the current, direction of the current is inwards, direction of the current is inwards. So this will be, this conductor will be a cross, this will be a cross, this also will be a cross. You can apply the Fleming's right hand rule, all these will be cross. Before this axis, right, this is the q axis, all of them will be the cross. Okay, all of them will be cross. And after this you will see here what is the magnetic field direction. So here I have south pole, right? And what is the direction of the torque? Here it is in the downward direction because it is clockwise. So here it was upwards, here it was upwards, here it is in the downwards direction, right? So that's why my thumb is in the downwards. Magnetic field is still on the right hand side, but I can see that the current is coming towards me. So this will be dot, this will be dot, right? So dot and cross, if I have not previously explained, dot means coming into the, going into the screen, dot means coming out of the screen. Okay, not, I will explain this in EMFT as well. When you will study EMFT from me, there also I will explain this more in detail. But how that dot cross came? So cross means basically you assume an arrow. So arrow, right? A arrow has a, like in its back it has a cross sign, and it seems like I'm throwing the arrow. If I'm throwing the arrow, that means it is cross, right? That means the arrow is going out from me towards the whatever in front. And if the arrow is coming towards me, I can only see a dot, right? I cannot see the cross, I cannot see the behind of the arrow, I can see the in front of the arrow, which is very sharp. That's why if it is coming out of the screen it is dot, if it is going into the screen it is cross. Okay, so all these conductors will be dot dot dot, and this will be cross before the q axis and after the q axis. Okay, now one important portion you have to understand is that what is the flux direction. So if it is a cross, right, again thumb will be now the direction of the current and my fingers will be the direction of the magnetic field. So for the left hand side, the direction of the magnetic field is in the clockwise direction. In the left hand side, the direction of the magnetic field is in the clockwise direction. Okay, so this will be the direction of the magnetic field for the left hand side conductors, right? So I will just draw one of them. So let me draw one of them. So it will be in the clockwise direction. Okay, clockwise direction. So yeah, that is the thing basically that we have to understand here. Now so this will actually affect. So if you see here, the magnetic field here it is opposing and here it is basically interacting. What will happen overall? This also will be, there will be a magnetic field, right? So this magnetic field and this one will cancel. Again this one also will be there and this one will cancel. So basically ultimately, right, overall magnetic field direction will be somewhat like this. It will be something like this. Okay, on the left hand side, the overall, what do I mean by it? So the magnetic field due to this conductor is like this. So magnetic field due to this conductor will be, I will draw in a different color if I have enough colors. So this will be the magnetic field direction now, same clockwise, right? So what will happen, this, right, this and this will cancel, same for here, this and this will cancel, same here. So overall the magnetic field will be in this direction. So overall the magnetic field will be somewhat like this. Okay, so it will be overall clockwise direction. So in the top right hand side it will be more stronger, and in the bottom side it will be more weaker. So more field lines will be passing on the top hand side, and less field lines will be passing on the bottom side. Okay, so overall the flux, right, resultant flux will be more towards here and less towards here. That is the crux. Okay, that is the important portion that you should like understand, right? So basically this will come back to, don't worry, we will come back to this later on. So basic crux is the, like, as this is the, let's say this is the magnetic field of the armature, and this is the field of the flux. Okay, so what I can say is overall flux, overall flux, overall flux, right, of the whole combination. So which color shall I choose? I am not able to figure out this one. So resultant flux will be like here I have more, like this is aiding, right, aiding phi f, and this one is opposing phi f. Okay, this one is aiding phi f, this one is opposing phi f. Okay, so uh, so here there will be less field lines in the bottom, and the top there will be more field lines. So resultant magnetic field lines will be something like this. Okay, for the right hand side also you can derive resultant field lines will be somewhat like this. So what happened? So actually what happened is previously my field lines were like this, but now my field lines have changed direction. So that is a problem, right? What are the problems, consequences, we will discuss. So in case of motor, again same thing, right? In case of motor, you can find out the direction of the current by using Fleming's left hand rule, not the right hand rule. So if it's a motor, right, and if the prime mover direction is given and the main field flux direction is also given to you, so what you can say is that what you can say is this is the main field line flux, and so what will be the direction of the current? So the rotation is like this. So for the left hand side conductors it is downward, so I will use the Fleming's left hand rule. So my direction of rotation is like direction of the conductor is downwards, movement of the conductor, and the forefinger magnetic field is on the right hand side, so this will be again cross. Okay, so generator again will be this as this time, remember, if I change the prime mover rotation direction, then this will be cross only. Okay, because this is generator and motor. So for generator and motor something has to change, right? So if I change the direction of rotation of the prime mover, then other things will be fixed, like the main field flux direction and the direction of the current will remain fixed. If you say, if you don't change the direction of the rotation of the motor and generator, then what will change? And if you keep the main field flux direction same, then the direction of the currents will change. Then here you will see these are dots and these are cross. You can do this exercise by yourself. Okay, you can do this exercise by yourself. Okay, so this will be here as the direction of the rotation of the prime mover has been changed, this will be cross, this will remain cross, right? This will remain cross, again the same effect, magnetic effect we will have, and this will be dot, like whatever I discussed in the top one, same effect will happen, right? So overall resultant flux will be like this. Okay, so this was like just a brief about the armature reaction. Now let's discuss few technical terms. Okay, the first one of them is the GNA and MNA. What is GNA and MNA? So GNA, also known as the geometrical neutral axis. It is axis where no EMF is induced in conductors because velocity vector is either parallel or anti-parallel to the magnetic field. Basically, it means that it is like geometrical. Neutral axis is basically, it is a geometrical parameter. Just you have to understand that it is located 90 degree from the d axis. Okay, d axis is what? Along the pole axis, right? So just you can ignore this statement. This statement you can ignore. Okay, not that important. I don't know why I have kept it, but it is basically 90 degree. It is a geometric parameter, 90 degree to d axis. So d axis is here, so it will be 90 degree. So GNA will be here. What is MNA? MNA is the axis where the resultant flux, including the armature reaction, causes zero EMF in the conductors. Okay, so this definition is very important. Okay, so if you see, one thing I forgot to say, this is the axis, right? So all my magnetic field lines will pass through here, but if I place a conductor here, will it cut any field lines? Will it cut any magnetic field lines? No. Here, no magnetic field lines. Here and here, right? Here and here, basically, no magnetic field lines will be cut. No magnetic field lines will be cut. Right? Okay, I don't have enough space. I'm sorry, I don't have enough space. No magnetic field lines will be cut. Okay, so it will be that axis where there is no magnetic field lines. Basically, if there is no magnetic field lines, there is no induced EMF, right, of the field axis. So in this case, in the first case, if I don't have any conductor, and if I just have a conductor, assumption is if the conductor is not carrying any current, that means both GNA and MNA will be parallel with each other. Now if I place a conductor that is cross, so the resultant magnetic field will be like this, right? This we have already discussed, correct? Resultant magnetic field will be like this. Okay, so if the resultant magnetic field line is like this, my GNA will not change. The direction of GNA, it is a geometrical parameter. So let me remove it, because you will, anyways, I know you guys will you guys will break my brain, okay, asking about that definition. What is that definition, sir? What is that definition? Okay, so let me just remove this anyway. Let me not keep it. Yeah, now it is fine. Okay, so in this case, in the second case, my GNA will be, GNA does not change, it is a geometric parameter, but my MNA will change. MNA will be the place where now the magnetic flux is zero. So it is always 90 degree to the field lines, right? 90 degree to the resultant field line. So actually it is here. So there is bit of mismatch between GNA and MNA. Whenever there is mismatch between GNA and MNA, it will cause problems. Because previously I discussed, right? We place our brushes along the axis where the magnetic field is zero, that is no, it does not carry any current. So here no current is carrying, right? It in the along the this GNA previously, and this was the MNA, there was no current, right? But now there will be current here because the resultant flux line is like this. So there will be current here. Current will be zero in this axis. So there is problem. So brushes actually should be placed along the MNA to minimize sparking, because there will be rate of change of current, right? If there is rate of change of current, a voltage will be induced. Due to that induced voltage, sparking can happen. That voltage can be very high. In this lecture only we have discussed about that. So in practical machines, due to armature reaction, the MNA will shift from GNA. Okay, so like these are the same things. GNA is the geometrical location, lies exactly 90 degree from the field axis. MNA axis where the resultant flux, that is a field flux plus the armature reaction, causes zero EMF, slightly shifted from GNA due to armature reaction. Okay, so yeah, GNA is fixed, MNA is this. Okay, so this is a problem. This is a problem. We will discuss what consequences we have. Before that, let me just discuss about one more term, that is leading pole tip and trailing pole tip. So leading pole tip is the end of the pole tip first encountered by the armature uh, during rotation. So if this armature is rotating in the clockwise direction, so I will encounter this pole, like tips are this, the tips meaning this edges, right? These are the tips. Where are all the colors, man? I'm not able to choose any colors. Okay, where are all the colors? Let me choose pink. Okay, let me add a color actually. Yeah, I am not able to see any color at all. What is happening, man? Okay, so here, right, we have this as edges. These are my tips basically. These are my pole tips. Okay, so out of this, which one is leading and which one is trailing? So the leading one will be the one that the armature will encounter first. So if I rotate in the clockwise direction, which pole tip I am encountering? This one, right? This one I will encounter first, right? If I rotating in this direction, if I am in this pole, right? If I am in this pole, if I am discussing about this pole, which pole tip will I encounter first? This one or this one? If I rotate in the clockwise direction, always I will encounter this pole tip first. So this will be the leading pole tip. So I will basically uh, like draw this to signify that my orange is the leading pole tip. For north pole, which one will be the leading pole tip? This one, right? If I rotate in this direction, always, no matter what, always I will encounter this pole tip first. So this will be my leading pole tip. Okay, so orange one is always the leading pole tip. Okay, and the let me choose another color. Let me choose this color, right? Now which one is the trailing pole tip? Trailing pole tip is the one that the end of the pole last encountered by rotating the armature conductors. So if I rotate in this direction, which one will I encounter last? This one, right? This one will I will encounter last. For the north pole, for the south pole, if I rotate, this one I will encounter first. This one will be the last one that I will encounter, this pole tip, right? So these will be my trailing pole tips. So the terminology is very important because we will use these terms. So this will be okay. So same thing here again. If the rotation of direction is opposite, so this will be the leading pole tip now. This will be the leading pole tip now, and this will be the trailing pole tip. Sorry, yeah, this will be the trailing pole tip, and this will be the trailing pole tip. So it will just reverse its roles. So this will be the trailing pole tip. This will be the trailing pole tip, and this will be the leading pole tip, and this will be the leading pole tip. Okay. So yeah, I hope you have understood this basic terminology. It's just a term. Okay. Now let's break down things in cases to understand the armature reaction even more. Although we have understood it already, but again to understand it in a full detail. So if I assume that only my my main field is energized, there is no current in the conductors. If main field is energized, along what direction the resultant magnetic field be? So assumption is right now, if only main field is energized, so my armature flux is 0. So my field flux is there, it is non-zero. So what will be the resultant flux? Resultant flux will be the, remember it is a vector quantity, okay, because it is dependent on direction, right? So resultant flux will be vector sum of the field flux plus the armature flux. Okay, So armature flux is 0, so it will be directly equals to the field flux only. And what is the direction of the field flux? Along the d axis. So this time the field flux is along this direction, right? This is my phi f. So let me do one thing. Let me just keep it here just to signify that it is above the d axis. I mean it is on the d axis, but to signify this. And my what do you call, the resultant flux also will be in this direction, right? Same direction. Okay, so I can write here, this will be the field flux, this will be the resultant flux. Okay, got it? Okay, okay. So this was the case 1. Now let's discuss about the case 2, where only armature current is present. So if armature current is present, what will be the direction of the flux? Okay, what will be the direction of the overall flux? That is what we want to know. So again, same thing, right? The direction of magnetic field, this will be in this clockwise direction, correct? Now if this is in the clockwise direction and this is also in the clockwise direction, so what will happen? Basically these will cancel each other out. So overall the resultant will be somewhat like this. Resultant on the right hand side will be in the clockwise direction, right? Okay, ignore my drawing. And on the left hand side the resultant will be in the anti-clockwise direction. Okay, left hand side the resultant will be in the anti-clockwise direction. So it will be in the anti-clockwise direction. So what will happen here? The field line direction is like this, right? So here, remember, okay, sorry, here there is no field line, so only armature current is present. So my field current if is 0. So again, if if is 0, that means what? That means basically if you see that I have only armature, so I have only armature flux, phi f is 0, right? So my phi resultant will be phi f plus phi a, but my this field is 0. So if field is 0, that means phi r will be phi a only. Okay, now what is the direction of the armature flux? So if you see, right, here the flux line is going downwards, here the flux line is going downwards, here the flux line is going upwards, here the flux line is also going upwards. So it is like just like a okay, on the outside it is upwards, on the inside it is downwards. Okay, so if I want to discuss on the q axis, which is 90 degree to the d axis, on the q axis what is the direction of the field flux? What is the direction, sorry, what is the direction of the resultant flux? I am only discussing along the q axis. So along the q axis what is the direction of the field flux? That is what I am interested in. Okay, so along the q axis, right, if I see the direction is downwards, so from the left hand side also it is downwards because it is clockwise, from the right hand side also it is downwards because it is anti-clockwise. So direction of the field flux on the q axis will be downwards, right? This will be my phi a and this will be equals to my phi r. Okay, now let's discuss if both the field windings are energized, then what will happen? Both the field winding is energized and the armature winding also is energized. Same thing, right? That due to the armature currents, the direction of the current, direction of the field will be like this. Okay, and the direction of the sorry, not this, direction of the right hand side conductors will be like this, correct? So along the q axis, again this time my phi f is not 0, phi a is also not 0. So this time my phi f is not equal to 0, phi A is not equal to 0. So my resultant will be vector sum of phi F plus phi A, right? So the direction of armature flux is in the downwards, phi A. The direction of the field flux is along the d axis, right? It will always be along the d axis. So it will be along the d axis. That is the field flux direction. Now, what will be the direction of the resultant? Resultant will be the sum, vector sum of these two. So it will lie somewhere around here, right? So this will be the resultant value. Okay, you can simply do the vector sum, right? Simply the vector sum you can do. And this, right? So actually my flux should have been along the d axis only, but how much has it moved? What is the angle? So this angle is known as the angle by which the flux has been moved, right? So this is known as the beta. Beta, what is beta? Beta is basically the angle by which the resultant flux has been moved, because it should have been along the d axis only, but the resultant flux has been moved, right? So this beta value is what? So I know one thing, that simple trigonometry if I apply, that my tan of beta will be the magnitude of sinusoidal, magnitude of the perpendicular upon the base, that is phi f. Okay, magnitude of phi a upon phi f, that's it. Okay, so this will be the tan beta. This will be the tan beta. Very important relationship. So again, phi f is the field flux, phi a is the armature flux. All these things you know already, right? So one more thing I forgot to mention, that what is the direction of the MMF? Direction of the MMF will be the same direction as the flux. What do you mean by it? Sorry for that burp. Okay, so I know that my MMF, right? MMF is equals to basically sorry, my flux, right? Flux is MMF upon reluctance. So reluctance is a like a scalar quantity. It is a scalar, right? So whatever the direction of flux, the direction of MMF also will be same, right? So this direction is also the direction of the field MMF, known as FF. Okay, so I will quickly define what does phi f, phi a, all those things mean. So slowly I will define it over here. So phi a is the armature flux. Phi a is the armature flux. Phi f is the field flux. Phi r is the resultant flux. My F FA is the armature MMF. FA will be the armature MMF. Don't have enough space, unfortunately. And my this FF will be the field MMF. And my resultant MMF will be this FR. Okay, so these are the things that is basically, that is what you have to keep in mind. That is what you have to keep in mind, right? Got it? Now the important factor, if the armature reaction increases, if the armature reaction increases, then what will happen? The phi a will increase, then the angle by which the resultant flux will shift will increase. So very important factor, that if my armature reaction increases, then my phi a will increase, the flux of the armature will increase, then the resultant will shift more towards phi a, so my beta will increase. So basically my tan beta also, basically my tan beta will increase, because tan beta is the ratio of magnitude of phi a by magnitude of phi r. So my tan beta will increase, so beta will increase. So it is a detrimental effect, right? What are the detrimental effects? That is what we will discuss. So these are the three cases that they have told here, and this is the resultant like summary, right? So now we will discuss what are the effects of armature reaction. So the first effect is very observable, that the MNA will shift, right? Whatever is the direction of the rotation, for in case of generator, if you observe one thing, that for a generator, right, I was assuming it to be generator only. So if you see from the starting itself, the direction of rotation for a generator is in the clockwise direction, and direction of rotation for a motor is in the anti-clockwise direction. So then only the conductor currents direction will be same. So that is what I am doing here. So here, in case of generator, the MNA will shift in that direction, in the direction of the rotation of the generator. In case of motor, it will be just the opposite. In case of motor, it will just the opposite. So in case of motor, the MNA will shift in direction opposite to the rotation of the motor. Now, one more thing. So flux distribution, what happens to the flux distribution? So the resultant flux distribution is something like this, right? More flux goes downwards. So what I observe is, in case of generator, the flux increases under the trailing tips, right? So what happens, actually this should have been more top, actually my bad, this should have been more top here, yeah, that is my bad, right? Yes. So what is happening ultimately is that the resultant flux direction will be somewhat like this, not this. Okay. So resultant flux, if you see, like now remember, this is my, for a generator, this is my what? This is my leading pole tip. This is also my leading pole tip. If you see, flux lines are not here. So flux lines decreases, not sorry, not that. Okay, you guys are very smart. I know you guys will cut this portion and then just put it. So flux line decreases under leading pole tips. If you observe here, the flux line decreases. Okay, and in the trailing pole tips, right, flux lines increase. In the trailing pole tips, the flux line will increase. That is for a generator. That is the effect. And now for uh, a motor, it will just be the opposite, because the rotation is opposite. So for motor, flux increases under leading pole tip and flux decreases under the trailing pole tip. Okay, so this is the direction of like this is the basically effect of armature reaction. Now first, I have already discussed that MNA will be shifted. So when does armature reaction happen? When there is armature flux. When there will be armature flux, when there will be currents in the armature conductor, because magnetic fields are generated. So basically the shift of MNA happens with load. If it is in no load, then there is no current, then no shifting will happen. But if it is at load, the MNA will shift. Now if MNA shifts, what will be the problem? If MNA shifts, then current will not be 0, along q axis. If current is not 0 along q axis, that means what? That means placement of brushes is wrong. Placement of brushes is wrong, right? That means there is a huge problem. There is huge problem. Okay, so that's why we don't we don't want this. We don't want our MNA to shift. Why? Because if placement is wrong, then there will be what? Commutation problem, right? Commutation problem, sparking, reactance voltage, commutation problem, reactance voltage already I have discussed. Reactance voltage, sparking, and like more detrimental effects are there. I will discuss about that as well. The overall magnetic flux density also will reduce, sparking, right? So that is also not good. It will be not symmetrical. Okay. What more can happen? Next effect that can happen is saturation, right? Why saturation? Because I told you that in one of the pole tip there will be more flux lines, in the other pole tip there will be less flux lines. So let's assume that, okay, these are four. So previously, if I have if I have assumed that there is no armature reaction, okay, or if I, okay, for no armature reaction, then there is no problem, field lines are totally uniform. And if I assume my core to be linear, then even if, let's say, there are more flux lines here, that is at the top, because this will be converted, this will go here, and there are more flux lines in the bottom for the south pole, correct? There will not be problem because my core is linear. So my, basically, the BH curve of my core, it will never saturate, right? No saturation. So if the flux line increases, then I have to just give more magnetizing current, and that's it. Okay, that's it. But what if there is saturation? If there is saturation, so if core is linear, right? If magnetic core is linear, increase and decrease under one pole shoe are equal. So average flux per pole remains same. So overall average flux per pole, right? So it does not matter if along here there are 5 lines and here there are 4 lines, but on an average, how many overall lines are there? 10 lines, right? So here, so not 10 lines, sorry, 8 lines. So here there are 5 lines in the top, and here there are 3 lines. In the bottom, okay, 5 lines in the top and 3 lines in the bottom. So, but overall, what is the number of lines? 8 lines. No problem, because core is linear, right? There will not be problem. I will show you why the problem will be if the core is saturating. So it does not matter, whatever is the amount of increase, that is fine. The field pole will allow this increase, right? But here there will be problem if core is saturated. Now if core is saturated, now if I say that I want to increase more flux lines here, and if the core has saturation, so maximum number of field lines that the core can pass is, let's say, 4 lines, right? Maximum number of field lines that the core can pass is 4 lines. So maximum is 4 lines, like I don't know exact value, but let's roughly say it is 4 lines. So if at max it can pass 4 lines, this cannot simply go here, right? Because resultant flux line, the armature will say resultant flux lines will be like this, right? So it will say more flux lines here, but the core will saturate. If the core saturates, what will happen? If the core saturates, then basically this flux line will be simply deleted, right? Because core will not allow, this field pole will not allow this many number of flux lines. Maximum only 4 flux lines can be present. Here again 3 flux lines are present. So here there is lower flux lines, here there is higher flux lines. So like that is another reason why the flux lines are like this, right? Another reason. So if core is saturated, increasing flux where flux density is already high is less effective. So the flux lines will not increase further, right? But decrease in flux will be more effective. So here currently I will have only 4 lines, and here I will have only 3 lines, right? So overall, what is the number of lines coming out of the pole? 7 lines. If overall I have 7 lines coming out of the poles, that means what? That means the flux, right? Flux has reduced, flux per pole has reduced. If flux per pole has reduced, the induced EMF also will be reduced. Okay, very basic thing. If flux per pole has reduced, the induced EMF also will be reduced. Okay, so if saturation is considered, the overall induced EMF reduces. So this is a same thing, it's written over here. This is a drawback of our this armature reaction. So these are the effects of armature reaction.